Okay, this class is all about, it's titled Classical Control Systems. Classical is a euphemism for old. Sorry, but it's to juxtapose with what we call modern control systems, sometimes called digital control. So I just want I want a disclaimer at the very start of class that if you're like me, you'll be excited about the stuff we learn about in this class. This was my favorite class in undergrad, the class that you're taking right now. But if you're excited about it and you ask me, Clay, where can I get a job that will pay me to do this? You have to go back like 30 or 40 or 50 years for that to be like a sensible question. What this class will give you is good fundamentals for doing control engineering, which is in itself a kind of a niche specialty, but you're not going to be working with Laplace transfer functions in an office setting. Like that's just not how it's done anymore. But like I said, it will give you a good foundation and starting point and jumping off point, because everything you learn is still applicable. It's just not done with like LTI and Laplace methods anymore. Okay. Sorry. All right, we are going to learn about how to model systems and how in particular controls engineers model systems. Just like in 228, the systems we talk about can be electric circuits, but they also can be other stuff, mechanical systems, electromechanical systems, hydraulic systems, all kinds of systems can be controlled. So maybe we should throw this out there. What is a control system that you encounter in your daily life? Anyone have a context for this class? Yeah, the thermostat, like the stat in thermostat is a regulation. It's trying to keep the temperature constant. And it's doing that by sensing the temperature of the room and either adding heat or taking away heat as necessary. That is what we call a regulator control system, trying to regulate the temperature in a room subject to disturbances. Disturbances like someone opening a window and letting the warm air out. The heater has to work harder. Or 41 people coming and sitting in the room and generating their own heat. And then a window opens. There's heat being generated, there's heat being lost. That difference, those differences are all called disturbance signals to the system that is the room. Any other examples? That's a good one. Cruise control is a classic one. It's literally in the name. It's trying to regulate the speed of the car. So what would be the reference input? I guess we're getting a little bit ahead of ourselves. I'll come back to cruise control. So I want to slightly differentiate between systems with feedback and controlled systems. This class is almost exclusively going to deal in this intersection area, but you should know that there are things in either non-overlapping areas. You can talk about open loop control. We have a whole experiment in 342 that covers open loop control, which means you basically do everything beforehand and hope it works. If that sounds like a bad idea, you and I are on the same page. And then systems with feedback, you can talk about systems with feedback, even though you wouldn't control them, like consider them as being under control or automatic control. What could be an example of that? Well, we'll talk about the DC motor example. I think that even without any kind of external controller, the DC motor has a feedback loop that kind of self-regulates. We'll talk about that in a second. Okay, so let's learn some vocab terms. We got an exogenous input here. I'm going to call this the reference input. What does exogenous mean? Yeah, from the outside. So this is a signal. I call it an exogenous input. That means it comes from somewhere else. Okay. And we've got the controller, and we've got the actuator, and we've got the plant. I think your textbook is trying to be a little bit modern and call this the process. So this could either be the plant, or I guess technically the process, although all of these systems are processes of themselves. And this word plant is a kind of leftover from the olden days when control systems and control theory was being applied to literally industrial plants. Like this was the steel mill or whatever that was trying to be controlled with actuation and control logic. Okay, and then here we've got the output. You're familiar with that vocab term? And what makes the focus of this class is this feedback branch. So what the sensor does, or the measurement device, is it takes the output as input and transduces it into a form that we can compare. Transducer, have you heard that word before? It's a fancy word for sensor. It means it takes some signal and transforms it into, usually in our context, a voltage. Okay, so like a microphone is a transducer from audio, from pressure to voltage. A electric thermometer is a transducer from heat to voltage. That is distinctly different than modulation. So modulation is when you take one aspect of a signal and change it according to another signal. Yeah. Okay, and I've represented the comparator here as a summing junction. Almost always we do something like this, where the reference input is given a plus sign. Sometimes this is omitted, where if it's not there, you just assume it's just multiplied by +1 because that means multiplied by nothing. And the feedback is almost always given a negative sign because this is equivalent to putting a -1 gain here and then a plus sign there. Okay. Either way, the implication is we're taking this signal and we're subtracting it from that signal. We're taking something that should be the output, right? If your measurement device is perfect, then this is exactly that, just with different units. We're taking the output and we're subtracting it from the reference. What name would you give this signal? Difference? Error is what I was looking for. What you want minus what you have, that difference is how wrong the output is. This is the key. This is the heart of understanding control systems, is that all of the stuff in this forward path doesn't get sent the reference. It gets sent the error. If the error is big, we need to do big things. If the error is small, we should probably be doing small things, like if we're just very gross terms. The controller is the subsystem that looks at the error and decides what should be done. So this doesn't really have a special name. This is just the controller effort or the output of the controller. The controller decides what should be sent to the actuator. The actuator is, as its name suggests, the thing that makes the decision into actual reality. Okay. So in the cruise control example, let's get back into there. In the cruise control example, what's an example of a reference input? Very conservative. Thank you. Yeah, I think 60 miles an hour would be a good reference input. That's what we'd like the car to be at. So let's say this is the set speed. In units of miles per hour. Okay. Let's skip around a little bit. What would be the sensor used by your car's cruise control system? The speedometer. What are the units? So like, let's talk about these signals then. Speedometer takes what units and transforms them into what units? Okay, it probably measures the rate of rotation of the axle or the wheel. So wheel speed in RPM. And then it converts that based on a known kind of axle diameter and tire diameter into the linear speed of the car. Yeah. Measured speed. Okay, this highlights a very important aspect of block diagram, which is what we're creating here. When you add or subtract signals, they have to be in the same unit. Right? If you had opted for a digital speedometer, whose output would likely be a voltage, then I would have said, I gotcha, because we can't subtract voltage from MPH. But you've seen through my ploy. And this is MPH, this is MPH, so this is the error in measured in miles per hour. Is the car going too fast? Is the car going too slow? Whatever is happening here and here affects this signal. So the controller is likely some circuitry that will take maybe even a transducer in itself that takes a mile per hour difference and converts that into a voltage, and then would convert that maybe through some filtering, maybe some amplification to decide what should be sent to the actuator. What is the actuator in the cruise control system? I think the throttle has to be part of it. The telling it to do more throttle would be kind of this signal. The telling it would be decided by this system. But yeah, I think the actuator should probably include the throttle. Like pretty much everything from where you put your foot, the pedal, all the way to the wheel, right? That all counts as actuation. Just a little bitty box. How are we going to fill that? No, this is like beauty of systems engineering. We can cram a lot of things in these abstract boxes, right? Because it's the throttle, the brake, all of that, the engine, the gearbox, the transmission, all of that takes the decision to go faster or slower and implements something to make you go faster or slower. In braking, it would be a force on the brake disc. In acceleration, it would be an extra torque on the drive axle. Okay. So can I just abbreviate that as drivetrain? That's an abstract concept that no one can really argue with. Drivetrain and brakes. So then the process, the plant, the thing that is being controlled takes, well, we said that this is going to be probably in units of force, like newtons, something like that. Whether it's a force on the asphalt or, I mean, in either direction, right? Forcing going forward, the acceleration, forcing reverse would be braking. I think this is the hardest one. What is the process? Yeah, I mean, the car is, I've heard worse answers. But we've already counted that here. Yeah. Motion is actually a bit closer. This is the system that takes a force and generates a rotation. This, I think, is just Newton's second law, right? Some of the forces or some of the torques equals ma, or maybe mv prime, if you like. So all of that stuff that you think of as a car kind of lands on the actuator block. And that old pesky physics 1 stuff is actually how that actuation comes into play and makes the thing that we care about. the wheel speed or the car speed.
So that's essentially saying that the car is the means by which this is taken.
Yeah, and there is like the reason why car is kind of right is because where does the M come from? That is the mass of the car. Yeah. Where should we include a hill? We're driving on flat ground. Cruise control is just making up for drag. You could imagine that as being kind of constant. But if that flat ground turns into a downhill, where should we account for that? Yeah. It's going to be a disturbance. It's going to be an extra force. In a downhill, it'll be a gravitational force down. In an uphill, well, in an uphill, it'll be a gravitational force down. There's no room here. Sorry. We'll go over here. So disturbance is typically also an exogenous input. It comes from the road. It comes from the path that you're traveling. You, as the driver or the car personified, don't control the hills. So the hills will come when they come. And so we need to be able to account for them in our system.
That's like every physical phenomenon then. Some like if you're moving a rat, if the rat is by force.
Yeah, but the key here is that there's feedback. And okay, oftentimes when a torque wrench is used, it's sensing the torque is being applied and it like lights up or it sounds when it hits the set point. Yeah. You as a human, you are often everything to the left of my arm. Like you often do that. When you're driving the car, you are looking at the speedometer, you are deciding what the error is, you're deciding you want more throttle or less throttle. Like human in the loop is what that's called. And as mentioned, I said this was a hill. It could also be wind. It's basically whatever produces an external force on the car in the direction that you're traveling. Sure.
Just because the disturbance is exhausted, meaning it can't happen. Well, like just for reference, you can still happen anywhere in that train, right? Like you have like a magnetic field type of stuff.
Awesome. We could have a disturbance here. We could have a disturbance here. We could have a disturbance here. Yeah. I wanted to highlight just a single reference and a single disturbance to highlight the fact that these are both exogenous inputs, but we as control engineers, we treat them differently. This is in some sense the good guy. We would like the system to respond well to this. And this is in some sense the bad guy. We would like the system to reject that disturbance. If the hill is tall or the hill is steep, we want the car to keep a fixed speed regardless of the size and the severity of this disturbance. Okay. Can you imagine how we want to react differently to changes in set speed versus changing it in disturbance? That's actually the heart of kind of what makes controls, especially classical controls, difficult. Is if we model a step change here versus a step change there, it's all in a loop. So you got to be careful about over designing for one and under designing for the other. This is all stuff we'll get into more throughout the quarter.
Where would that fall?
Tapping the brake?
Sorry, yeah.
I mean, that would basically eliminate all of this, right? If you turn the control system off, then you would be braking probably that link. The speedometer is still going to be measuring. You might have still stored a reference, but the controller, whatever decides, doesn't get sent to the actuator. The actuator, the brake pedal, respects your foot above and beyond whatever the control system tells it to do. Yeah. Ideally, yeah, ideally. Yeah, so we try and track the reference and reject the disturbance. That's one sentence to encapsulate the last 10 minutes.
So, like,
Yeah, so I haven't put, is this time domain, is this S domain? This is basically just conceptually what is the order in which information is transferred throughout the system. We will deal with these block diagrams in the Laplace domain pretty much exclusively in this class. So what I mean to say is that we're going to make all kinds of LTI assumptions, but the signals themselves are definitely time varying. If the signal wasn't time varying, it would be a really boring control system. And so if the input is time varying, if either of the inputs are time varying, then that guarantees that the intermediate signals are going to be time varying as well. Never mind the fact that we don't just have inputs to deal with, we have initial conditions. Remember zero input response? That's still a thing. Okay, good job, people. This kind of gets at like how controls is one of the entry points into like system design, because we get to start talking about systems as more abstract objects. But I want to kind of walk you through. I'm going to basically skip over step one. This is something that you'll talk about more in your senior year, like 409, 460, 461. Functional block diagram, that's pretty much what we just did. Functional or abstract block diagram, this is basically saying what are the major important subsystems and what are the signals that travel between them. We're not making any assumptions about LTI or Laplace or anything. These are just, we have a speedometer. It changes real speed into sense speed. That's it. And the next steps will be something like take that functional block diagram and dive into it and try to model it with your physics and your math knowledge. That's where I'd like to go now. So let's talk DC motors. How many of you have taken 295, 255? Okay, I hope what I say will be vaguely familiar, but by no means do I expect you to have taken AC and DC machines. Okay, so let's talk about the armature of the DC motor. This is a reasonable circuit diagram for that armature. We are generally able to control the voltage across the armature, which I'll call V sub A. The armature consists of a whole bunch of copper windings, which is going to have some resistance and some inductance. And okay, here, I'll check your 255 knowledge. What is this? Good, the back EMF. Something about Faraday's law, something. We've got spinning magnetic fields, and the idea is that the faster the motor spins, the more back EMF is generated. EMF is an old-timey term for voltage. So I'd like to model the back EMF as being proportional to the motor speed. All right. We have a loop with a couple of voltages and some impedance elements in it. We are going to see a current through there. And I would like to model, this is another, I think, a 255 topic. I'd like to model the torque applied by the motor to be proportional to the current through the loop. So I is the armature current, and tau sub m is the torque generated by the motor. And these Ks are simply proportionality constants, saying that the voltage here is linearly proportional to the speed, saying the torque here is linearly proportional to the current. More current, more torque. Okay. So let's take our free body diagram. Sure. And let's say that the torque generated by the motor is going to twist this shaft. This is the shaft of the motor, the rotor of the motor. The tau m is going to say act in this direction. We'll say that there is some moment of inertia associated with the shaft. It could be just the mass of the shaft itself, or it could be some load attached to it, a mechanical load. All that J. And let's say that there's also going to be some friction, and we'll say that friction acts against the direction of motion. So this will be Kf, or I'll just call it tau F here, torque due to friction. And let's just give a reference, like if it spins this way, that is positive speed. If you do your right hand, we'll say this is positive direction. Okay, I would like you to take this free body diagram and write out Newton's second law, given that notation. Good, you've all memorized F equals ma, but have you heard of its cousin, torque equals J alpha? Sum of the torque is moment of inertia times angular acceleration. This is Newton's second law in our rotational frame. Okay. So we need to decide what is a positive torque and what is a negative torque. I think based on the fact that this omega m is drawn as this way, and that matches this tau m, that we should call tau m as a positive torque and tau f as a negative torque. They have to be different signs because they're acting in different directions. And rather than alpha, I think we should write omega prime, or derivative of omega. I'd like to make one simplifying assumption here, and that is the friction is going to be proportional to speed. As the shaft spins faster, it experiences more friction. This is called a viscous friction model. So our tau f is going to be, say, proportional to speed. As shouldn't surprise you, at the end of Newton's second law application, we've got a differential equation. In this case, we can consider tau m to be the, what do you call it, the forcing function, and omega m to be the output variable. Okay. So the next thing I'd like you to do is to get the Laplace transfer function from tau m to omega m. It's only been 2 weeks for about half of you. I should point out, when I give you these little mini assignments, they're not quizzes. Like, you can ask for help. That's part of learning. No. The other way around, but yeah. Don't do it in the time domain.
Right.
Do it in Laplace.
I'm gonna switch it to
Okay.
then I'm gonna have like a 1 over tau m, like float around, right? Or how do I? Like,
Do the
they're like kind of like coupled with that, right? No.
do this Laplace transform, and then I'll come back and help.
Yeah. I didn't forget. Okay, I didn't. So we're assuming that is that a tau m right there on the right side?
Yep.
Okay, so tau m, that's what we're saying is the variable,
The input.
okay,
Yeah. Good. We don't know the form of tau m, so all we can do is say tau m in the time domain has some Laplace transform. Call it tau m of s. If you like, you can make it a capital tau m of s. We also, if we don't know the input and we don't know the exact form of the output, but we can do the same thing. The output waveform will have some Laplace transform, call it omega m of s. And once we do that, oh, and then Laplace transform is linear. So the Laplace transform of a constant times a function is that constant times the Laplace transform. And then Laplace does what to initial condition, sorry, to differentiation. This is the property that you learned, df dt becomes f of s minus f of 0. If we're after a transfer function, we're assuming 0 initial conditions. So a differentiation in time is a multiplication by f. So at this point, I can pull the omega m out of both of these terms. I get js plus kf. I can divide through by tau m. I can divide through by js plus kf. Get 1 on js plus kf. Okay, so that is questions on that. I sometimes forget that not all of my students live, eat, sleep, and breathe Laplace. Sometimes. Cool. So
far we've been stressful.
this is how torque transfers to speed. Okay, so in fact, what we're going to do is we're going to put this in its own little micro block diagram where motor torque is here, transfer function goes in the box, and output is here. Okay. So this is the anatomy of a Laplace block diagram. The input goes on the input side, the output on the output side, and the transfer function goes in the box. So let's go back up the chain. Where does tau m come from? But more specifically, it comes from the current. It's proportional to the current. This is in the time domain, but if I Laplace this, if Km is constant, then it's the same, like the transfer function from current to torque is just Km. Right, literally, Laplace transfer functions multiply inputs by transfer functions to get output. So if I multiply input, I should be more specific. This is I of s. This is tau m of s. This is omega m of s. Please don't multiply time functions. That's a big no-no. If I multiply I of s times the motor torque constant, I get tau m of s. That is exactly what would happen if you Laplace transform this equation. Where does I come from? Good. We need to do circuit analysis. We need to do KVL or Ohm's law or however you like to get I from VA. So where can we fit that? I'm going to squeeze it in right here. Yeah. Transfer functions, one of their main jobs is to transform units. Right? The units of Km would be in newtons per amp. Yeah. Probably the units of this one would be something like rads per second per newton, I don't know, something like that. Okay, so let's do, what do we got? Ohm's law. The voltage difference across this RL series is going to be VA minus KB omega M. So delta V over Z is going to be VA minus KB omega M. We might as well do this in Laplace, right? So this R becomes R, this L becomes SL, and now we can properly talk about Z of S, as long as we have delta V of S, yeah? Okay, so the series impedance is going to be R plus SL. This will give me the current in the S domain. Voltage, right? It's literally next to a voltage source. So this KB times omega M has got to be in units of volts. And there's a difference here. Like there is a subtraction, that's what I'm trying to say. So I think, how should we model that subtraction in a Laplace block diagram? A summation, but one of those terms is being summed. Hey, it's our output, which gets fed back. So if I put VA of S here, then I need KB as a transfer function there. And what is this signal? Omega M. I'm formulating the numerator. I haven't gotten to the denominator yet. But I can formulate the numerator algebraically by just doing this guy minus this times omega M. But I have omega M already over here. All right, just under the gun, what goes in the blank? What fill in the blank? Good, 1 over R plus SL. Awesome. This is this signal, which again isn't really the error, which is why I think that this DC motor is one of these systems. There's feedback, but nothing's being controlled, right? We're not setting a set point or anything like that. So this numerator is this. If I divide that by this guy, I get the current, and then we can close the loop. Okay. So we have just drawn a Laplace block diagram that takes the armature voltage as an exogenous input and produces the speed of the shaft as the output. We'll talk about what to do with this on Friday. See you then.